Hello and welcome to the first YouTube tutorial for nandland.com. Today I'm going to talk about what is an FPGA, but there's going to be more videos in the future where I'm going to go into much more detail about how FPGAs work, what languages are used to program them, so definitely subscribe to my channel and make sure that you watch more videos to learn much more about FPGAs. Today I'm just going to start with the basics. So first of all, FPGA stands for Field Programmable Gate Array. Now, FPGAs have been around since the mid-80s, and since then, like any other technology, they have grown significantly more complicated. So it's best to take a look at what things were like in the 80s and talk about where we are today so you can get an idea of the technology. So an FPGA, way back in 1985, was very, very simple. It was essentially a chip, an integrated circuit that the FPGA designer could design physical circuits with. So back then circuits were very simple and you could only do a limited amount of things with them, but they did enable some interesting things. So the first thing I'm going to talk about is our low-level gates, AND gates and OR gates. You may have heard about this. If you have, this will be a little bit of a repeat for you, but for those of you who don't know what an OR gate is, I'm going to explain it now. So, an OR gate is a device that looks like this on a schematic. It has, a simple OR gate has two inputs and one output. So, when either of your two inputs are high, or a 1, then the output will be a 1. So an OR gate falls into the category of Boolean logic. Boolean meaning 0 or 1, true or false. So those are all the same ways to say the same thing. So your input can be a 0, it can be a 1, this can be a 0, this can be a 1, this can be a 0, this can be a 1. Those are the states that this can be. Now, as I explained, an OR gate will be, the output will be a 1 if either of the two inputs are a 1. So, for example, if both my inputs are 0, my output will be a 0. If this one now becomes a 1, my output becomes a 1. If this input changes to a 1, the output stays at 1. So, knowing that, you can actually draw what is called a truth table for an OR gate. A truth table says, what are all your possible inputs? What is your output? So we can do a truth table for an OR gate. So it looks like this. Input 1, input 2, output. Now the combinations for your inputs are binary inputs, 0 and 1, true and false. And I'm going to go through each one of those options now. So this can be 0, 0, 0, 1, 1, 0, 1, 1. Now again, as I explained, if there's two zeros on both of your inputs, the output will be a 0. And then if either of your inputs are 1, then the output will be a 1. So either or, which is why it's called an OR gate. So that's what the truth table looks like. That's an OR gate. There are many other gates. There's AND gates, NAND gates, which I have a particular affinity for. There's XOR gates, NOR gates, there's much more. So I do want to just introduce this to you now, just to give you an idea of what a gate is. So when I say gates, you have an idea. So that's an OR gate. Now, going back to what is an FPGA. In the 80s, like I said, FPGAs were very, very simple. So they could only do a certain number of gates in a particular device. But that's what they all do. They all implement those gates, AND gates, OR gates, on a device. So, for example, if I have some device with, let's say I have four inputs and one output, I can do the FPGA is essentially a black box that I can put anything I want inside of it. I can put OR gates, AND gates, I can put anything. So the FPGA designer might want to draw some circuit like this, and then another one that looks like this, and then maybe has an OR gate over here as well. In 1985, this would have been a perfectly viable FPGA. So here's your FPGA right here, and here's what's inside. This is an OR gate, this is an OR gate, this is an AND gate. So you have 4 inputs and 1 output. Now, not too complicated, not very special, but in 1985, this was pretty powerful. The interesting thing about FPGAs is that they are field programmable. That's what the F and the P stand for. Most of them are field programmable. Some of them are fixed. But what that means is that in the field, when you are using them, you can actually reprogram this. So if the designer decides, oops, I don't want this to be an OR gate, I want to rewrite it and make it an AND gate, they can do that. It's field programmable. And it's an array of gates. Gates, gates, gates. So at a very low level, this is what an FPGA can do. Obviously, the technology has improved significantly since 1985. So nowadays, this is very, very trivial to do. FPGAs have gotten way more complicated. They can do tens of thousands, hundreds of thousands of gates inside of one device. Whereas back in 1985, they could only do a few dozen. So today, FPGAs are found in surprising places, places you probably don't think about, but in general, they're found throughout the defense market, in radar systems, in missiles, military systems. They are found in medical devices, they're found in MRIs, CAT scanners, you can find them there. The telecom industry uses lots of FPGAs. Your cell phone towers use pretty high power, powerful FPGAs to do a lot of the signal integrity, signal decoding stuff, sending Ethernet packets around. A lot of the internet backbone is controlled by FPGAs. Your cable box inside in your living room might have an FPGA inside of it to do some of the DVR recordings. And the finance industry uses them too for high frequency trading. So if you're kind of getting at what they're powerful for is things that are done really quickly. So FPGAs are fast. That's the big benefit of an FPGA. Fast and reprogrammable. So if you have a cable box that you want to change how it works slightly, you can actually reprogram it on the fly. So why are they fast? Good question. FPGAs are fast because they can do a lot of things in parallel. Now this is very different from a normal processor that you might be used to. Processor that runs your computer, for example. Processor that runs your computer might be a very fast Intel processor in the 3 gigahertz range. 3 gigahertz means that it runs 3 billion operations per second, cycles per second on your processor. So, but the interesting thing about a processor is that they only run one operation at a time in that particular processor. You can't do operation number 3 until you've done 2. You can't do 2 until you've done 1. So they're sequential. You have to do them one at a time. Now this is very different from how an FPGA works. An FPGA can do a lot of things in parallel, which when I drew that circuit on the whiteboard here, you kind of get an idea for that. Both of those gates are working in parallel, if you can think about that. So if you had a huge number of gates, all those gates could be working in parallel on the same data at the same time. And what that affords you is the ability to send a lot of data through an FPGA at a very, very fast rate. So things that use video is a ton of data. HDMI interfaces use tons and tons of data. FPGAs are used to process all that data in real time because they're fast. That's how they work. So this will become more clear the more that we work with FPGAs. you'll start to see some of the benefits, but take it for granted now that FPGAs are very parallelizable versus a normal processor that you might be used to is very sequential. So I want to show you what an FPGA might look like today. I have one here. This is the FPGA in the middle of the board here, and this is called a development board. It's got just one FPGA on it and some I/O, some input-output around it, and the user can program the FPGA to do different tasks and play with it and create whatever projects you want to create with it. You'll notice that on this particular board there are a large number of pins on this connector here, here, and there's the same connectors on the sides. The reason I point this out is that this is one thing that FPGAs are pretty good at, is they have a lot of connections to the outside world. They have a lot of I/O. So if you have a lot of interfaces that you need to maintain for a particular project, FPGAs can be pretty good with that. This particular FPGA has over 100 pins brought out to connectors right on this one development board, but there are some that have over 1,000 pins, which is a very large number of pins to work with. The last thing I want to say about FPGAs is that they're a lot of fun. They are equivalent to building a project, building something with Legos. You're building things that are at the gate level. The smallest possible level is the level you are working with. So you can imagine starting small and building up and making pretty complicated stuff with them. There are two languages used mainly today for FPGA development. The first is VHDL, and the second is Verilog. They are both powerful languages. They're different from a language like you might use like C or Java because they are targeting a system that, again, is parallelizable. So I'm going to get into exactly how VHDL and Verilog are different in future videos for nandland.com, but just know that these are the two main languages to use. In general, I would recommend using whichever language your business uses, whichever language your university uses, or whichever language your country uses. I can tell you in the United States, in the defense industry, there's a lot of VHDL. I can tell you in England uses a lot of Verilog. There's different countries in the world where these two languages vary in popularity. So find out what's popular in your area and learn that language first. You're going to learn both of them at some point, but if you want to focus on one, find out what's popular first. So hopefully that gives you a pretty good idea of what is an FPGA. I'm going to have lots more videos going into a lot more detail, so definitely subscribe and stay tuned. Thank you.